Okay, so I now want to spend some time discussing Leibniz's contribution to calculus and the way that he viewed things. So, whereas Newton decided that he wanted, or not decided, whereas Newton was sort of thinking of everything in terms of motion, and things are moving and everything is related to motion, and kind of developed calculus that way, Leibniz took another approach, an approach that's also very familiar to us, which is to take the x-axis essentially, or maybe not even the x-axis, but take whatever object we're thinking about and cut it up into a bunch of pieces, and then we're going to analyze each piece separately. So one way that we can sort of think about this would be the following. What if we take a curve and we cut it up into a bunch of different pieces? So take a curve like this, and if this is the x-axis and this is the y-axis, what we want to do is we want to chop your x-axis up into a bunch of pieces, and then the y-axis, the y that changes in y as well. So like from here to here, let me make this a little bit bigger. From, let's say, here to here, this would be dx, and then this distance here would be the corresponding change in y. So this is the way that Leibniz started to started to think about things. And nowadays we probably would call these delta x and delta y, but again, we're thinking about these as being infinitely small. So we're going to chop up the curve into infinitely many pieces. That's sort of the idea behind what's going on here. Okay. So what can we do here? Let me make sure. Yeah. So what does this allow us to do? Well, the key idea is that dy dx, dy divided by dx, is the slope of the tangent. And I drew a triangle similar to this in the previous video, so I won't draw the whole thing again. But again, the idea here is that if we have this tangent like this, okay, then this distance right here is dy, but really if we extend it a little bit, we can kind of consider this whole leg there as being dy as well. And by definition, the slope of the tangent line is going to be that distance divided by that distance. And so the slope of the tangent line is simply the infinitesimal change in y over the infinitesimal change in x. Okay, the infinitesimal change in y over the infinitesimal change is x. And so dy and dx, these really are sort of representing, in some sense, quantities, and dy dx is ratio. And so since they are representing quantities and ratios and things like that, then we can, or at least in some sense we can, and Leibniz certainly did, treat them as such and do the various algebraic things that you can do when you're dealing with quantities such as that. So we're going to talk about that next. Okay. So, of course, if we're going to compute things, then we have to have rules. We have to know how to compute things. So, if this is to be, if Leibniz's method here, if his interpretation is going to have any value at all, then we need to have some way to be able to compute things with them. So, I'm going to do a couple of computations here, just so we can get a feel. It's going to be very similar to what Newton did, the way that Newton talked about things. So let's think about, okay, so dx squared, okay, if we think about what this is going to be like, okay, so what we're going to work with, before we even get here, we're going to look at x plus dx times x plus dx, and when you just do ordinary algebraic operations here, you're going to get x squared plus 2dx plus dx squared. Okay, so what this means is that dx squared is going to be equal to x squared minus this. And so this is equal to 2 dx plus dx squared. Now at this point, Leibniz is not dividing by dx or anything like that. He's just saying that if dx is small, then dx squared is if dx is infinitesimally, wow, I realize I made a mistake here. This is 2x. If and so this would be 2x as well. If dx is infinitesimally small, then dx squared is basically 0, at least compared to dx, and so we're going to forget about that, and so we're just left with 2x dx. And then from there, you can see exactly how the argument for the more general power rule that I have here on the slide would be. Okay, now at first, when doing the product rule, Leibniz at first thought that when you looked at dxy, that this is going to be equal to dx times dy. Kind of makes sense. It seems like it might make sense. I mean, it doesn't make sense because it's wrong, but that's obviously a very reasonable thing to think about. But it's not equal to that. It's equal to what I have listed here, and I'll show you why. But again, many of you have probably heard the story that Leibniz got the product rule wrong. He thought that, in our modern notation, fg, the derivative of fg, he thought would be the derivative of f times the derivative of g. Or, to put it in differential way, this would be d of xy is equal to dx times dy. And as we'll see in just a moment, that's not true. Now, apparently what happened is he thought it was true, and he wrote some more, and then once he got to the power rule, that's when he realized, oh wait, hold on a second, this isn't working right, because if his version of the product rule was correct, in other words, dxy equals dx times dy, then you could apply this to x. Now he knew you could apply this to x squared, and you would get dx squared is equal to dxx is equal to dx dx, which is equal to 1, but this is not what dx squared is, okay? So in other words, he got the wrong product rule, but he realized it was wrong. I don't know exactly when he realized it was wrong, but certainly when he thought about it in the context of the power rule. You could tell definitely from there that either the power rule is wrong or the product rule is wrong. And it actually seems that it's the product, well, we know that it's the product rule that's wrong, but it seems that he just thought that something was true, and he said, oh, this is true for the product rule, but actually it's not true. He kind of had a moment where it was like, well, this is obvious or something, when in fact it was not obvious because it was wrong. So sort of a word of warning there, I guess. Anyways, so dxy, well, again, what we're going to do, x plus dx times y plus dy. This is just the change in x times the change in y. And then again, if we do algebra here, we're going to get xy plus x dy plus y dx plus dx dy, dx times dy. Okay, now what we're going to do then is do xy minus this. That's xy minus the change in xy, and we're going to get that dxy. This is going to be equal to xy minus this, and so the xy's cancel, and what we have is x dy plus y dx plus dx dy. Now this isn't dx squared like we had before, but again, if dy and dx are both very small, the dx times dy is also very small. It's like 1/2. 1/2 is small in some senses, but 1/2 squared is even smaller. And this becomes more and more true as the quantities go to 0, which is exactly what happens in the context of infinitesimals. And so that just goes to 0, and then what we have left is x dy plus y dx. And so this is the product rule sort of stated in differential form like this. And speaking of differential forms, though forms kind of using a different form has a different meaning in both of those phrases. This is exactly how we still compute with differential forms. So even nowadays, when we're computing with differential forms and kind of doing stuff like this is exactly what we're doing. So again, similar to what we saw with Newton, what they were doing was not very precise, but it worked, and it can be made precise, and it's essentially exactly how we think about things nowadays, except we just have this sort of precision that sort of undergirds everything and makes us more confident that what we're doing is not crazy. Okay, now what about tangents? I've got some strange typo here that I can't quite figure out what I think it should say dy equals dy dx. So dy is equal to dy dx times dx. So remember, this is the slope of the tangent. That was one of the very first things that we saw. Now, why do we have this relationship? Like, why is this true? Well, what this is saying is that an infinitesimal change in y is equal to the slope of the tangent line. So that should say slope of tangent line. The slope of the tangent line times the arbitrary, or the small change in x as well, the infinitesimal change in x as well. And this is very similar to how Newton thought about things like this as well. The change in y is equal to the speed or the velocity times the change in x, or the change in time. That's sort of the way that's very similar in a certain sense to the way that Newton was thinking about things. So in other words, if we have something like y is equal to x squared, then using the rules of differentials, we're going to get dy is equal to 2x dx, and so that right there is dy dx. I mean, if you just divide both sides by dx, you get that's equal to dy dx, and so this is going to be the slope of the tangent line. Okay, so again, this is exactly this is different way of thinking about things, but also in some ways similar to how Newton was thinking about things as well. Okay, so one of the cool things that he sort of did was to solve this old problem, this somewhat old problem. Now, this is one of the first differential equations that we solve in a modern differential equations class. Okay, and so for us, this is easy. This is going to be a very easy differential equation to solve. But the reason that it's easy is essentially because we've already, when we are thinking about it now, okay, we have the benefit of sort of knowing what the answer is, and I'll try to explain what I mean by that. But what was asked is to find a curve. I think maybe it's off the page a little bit. No, find a curve whose subtangent is equal to a constant a. Now, I've mentioned subtangent before, but I haven't talked so much about it. I haven't given a very good definition of what it is. So let's say this is the x-axis, this is the y-axis. Let's say this is your curve. You're looking at this point right here, and we're going to look at a tangent line like this. This distance right here, that is t. That is a subtangent line. And then again, if we look at the differential triangle, sort of zoom in here, and we get something like that. Well, we know if this is y and this is t, we have y over t, and by similar triangles, this is equal to that over that, which is exactly dy over dx. And so what this tells us is that the subtangent t yeah, so I guess we could solve this for the subtangent. Sorry, I blanked a little bit there. We could solve for the subtangent and get that the subtangent, using our notation, so using Newton's notation here, would be y prime divided by y. But what we have now, if you look at this, we have y over t is equal to dy dx. Okay, and so what we want to do is we want to find a curve whose subtangent is a given number. I'm going to say, let's call it a. I'm not saying that, that's what the book says. So we're going to have y divided by a. And if we rearrange things, we can write this as a dy equals y dx. Okay, now what Leibniz now does is say, okay, let's imagine that dx is a constant. Okay, so we're splitting up the x-axis into a constant constant width subintervals here. Then if this is equal to whatever it is, we can write this as y is equal to k times dy. That y is equal to k times dy. Okay, so y is equal to k times dy, where over here k would be equal to something like a divided by whatever this constant value of dx is. And so now what he notices is, okay, so dy is like the difference in y. So if you think about x's increasing sort of in a discrete manner, then the corresponding y values are also going to increase in a sort of discrete manner. And what this says is that y is proportional, y is equal to a proportion times its difference. Okay, what this means is that the difference, I guess you could say, is proportional to y. In other words, we have a geometric progression for y. Okay, so y goes up by a factor of k, 1 over k each time. That's what this is saying. dy is equal to y over k. Okay, so then what he says is that in a case like this, and then of course he imagines dx going to 0. So in a case like this, when you have a geometric progression, what this means is that the steps themselves, that is the x, are in a logarithmic relationship to the outputs. That is in this case the y values. Okay, so in other words, what he says then is that there is a logarithmic relationship between x and y, or what we would call today an exponential relationship, but obviously those are the same things, just sort of depending on what your perspective is. Okay, excuse me. Okay, last thing that I want to talk about is going to be integration. So let me sort of introduce something here. So let's say I have a sequence of numbers, yk, I'll say y sub I, where I will go from 1 to infinity, and he's always going to take the first term being equal to 0. So I have a sequence of numbers like this. Okay, now there's a couple of things that I can do with this. I can form the sum sequence. So this I'm going to call S sub k. S sub k is going to be equal to the sum k equals I equals 1 to k of yi. Now, whenever I have a sequence, whether it's the y's or the s's or the y's, I can define what's called the difference sequence. So I'm going to call it delta sub k, and this is simply going to be S2 minus S1, S3 minus S2, and so on and so forth. Now, for the particular case where the SKs are this sum sequence, well, let's think about what's going to happen here. S2 minus S1, well, this is the sum going from 1 to 2. So this is y1 plus y2. This is y1. So this is just equal to y2. And then this is going to be equal to y3. And this is going to be equal to y4, and so on and so forth. Okay, so kind of in terms of sequences, if we have this sequence of sums, I equals 1 to k, yi. Okay, what we get when we do this is simply going to be the y sequence like this. Maybe I'll put like this. Okay? That's what we're going to get from the different sequence. Well, what this is in terms of, if we now sort of don't think if we think in terms of infinitesimals and letting things get arbitrarily small, this is going to be d, the integral y, is equal to y. Okay, now the problem here is that this right here is starting to really not make any sense. Because y could be an infinitesimally small number, or sorry, y could be, we can add up an infinite number of things here and still have infinity. So this right here, even before we get to the d, this notation right here, the integral of y, doesn't make any sense when we have it in this way right here, and we think about y as just being a small increment from the one before. Okay, this doesn't make any sense because again, if we just think about adding up successive, if we think about adding up successive numbers, and all we're doing is just making more and more numbers, or just adding more and more numbers to that sum, then that sum is going to be infinite. And so in the limit, or that sum is going to not converge. And so what I'm trying to say here is what this kind of represents in the way that Leibniz is thinking about it is when we pass from here to here, this is a sum that has finitely many terms in it, finitely many y terms in it. This is a sum that has infinitely many terms in it. But each term is, going to be one of the corresponding y values in, like in the graph of a curve. Okay, it's just going to be the y value. That's what we have here, the y values. Okay, so what we see, what's going on is we're not actually adding up like areas of rectangles, which is what we're thinking about. We're just adding up the heights of rectangles. So this is the heights of rectangles. This is an infinite sum of heights of rectangles, which is in general not going to converge. Okay, so now how he fixes this is just say, okay, well, what we need to do then is multiply this by an infinitesimal, and so now the sequence is y dx, and we're going to have the same thing over here as well. Okay, so this is sort of the rule, this is what he uses to be able to integrate something, or to be able to find the area under a curve. Well, okay. So then we have d y dx is equal to y dx like this, okay? And again, sort of graphically, I'm not going to draw the picture because we know what that graph looks like. Y times dx, this is the height of a rectangle, and we think about this as being the width of a rectangle, right? And so now what we want to do when we want to compute the integral, let's say we want to compute the integral, let's see what example I have here, x squared dx. Okay, so remember, it's like compute the area under the integral, or under the curve, or under the graph of y equals x squared, or under the curve y equals x squared. This is how we represent that, right? And so now the question becomes, which function has differential equal to x squared dx? So which function has differential equal to x squared, which function has a differential that's equal to x squared dx? And of course, that's going to be x cubed. That's going to be x cubed. Okay, and so now the integral, if we go, let's say, from 0 to 1, or let's say 0 to 3, is going to be equal to 3 cubed minus 0. Okay, and again, the way that he conceptualized things, the first term is always going to be equal to 0. All right, so that was a brief look at the way that Leibniz viewed calculus. You can definitely see that there are well, it's obvious that there are differences between that and the way that Newton thought about calculus. But I also think there's a lot of interesting similarities as well, especially now that we have the benefit of being able to look back and seeing exactly how things develop.